Alright, so I'm really hoping there's audio in today's video. The little slider thing here is telling me that there is, so I'm gonna have faith. I wanted to quickly take up today's work, so you could, go through those questions kind of in your own time or at your own pace. So let's give that a try. So this is the 3.5, a little more stoichiometry with enthalpy data lesson. So this just is work to practice related to what we did in class today. So what do I do? tell me the audio died in the middle there. If the audio's been dead this whole time, I will cry. Oh, will I cry? Oh, I'm having audio issues. It's my own fault. It's my own fault. I've got nobody to blame for this but myself. Okay, still working on tech issues here, team. Okay. Yarg. Well, whatever, you're going to have to be patient with me. I'm doing my best. It's the best I can do. All right, so grams will cancel with grams. And then I don't want to talk about moles of sodium hydroxide. I want to talk about what? Pray tell. Well, I want to talk about kilojoules of energy. And luckily, looking at this, we know that 1 mole should release 44.511 kilojoules of energy. And so now we can just do this calculation. 28.41 times 1 divided by 40.00 times 44.511 divided by 1. And we will get 31.639, and I think we have 4 sig figs. So this should be 31.61 kilojoules of energy. Therefore, 31.61 kilojoules of energy will be released. Now, hey, this question is actually a calorimetry question. If we assume that this was actually dissolved in 350 mils of water at 28.2 degrees Celsius, we can find the final temperature, because we know that Q equals MC delta T. And so let's work this out. Q, well, we just figured out Q, 31.61 kilojoules. M, what's the mass of water? Well, we know we have 350 mils, and we know that a milliliter of water weighs a gram, so we know we have 350 grams of water. And again, the water is the stuff changing temperature, so it's what we worry about. C of water, geez, I don't remember. Gotta look that up. So let's go back to specific heat and find the C of water. C of water is 4.186. 4.186. 4.186. Joules per gram Kelvin. Okay. Right. Yeah. And then we got to watch, because this up here is in kilojoules, so we're going to want to convert. That's 31,610 joules. Right? We'll be careful there. Q is 31,610 joules. And delta T, well, that's what we want to know. So, let's rearrange this to find delta T. I'm going to have to divide by M and divide by C to get rhythm, but of course what I do to one side, I must do to the other. So, delta T is equal to Q divided by MC. And so delta T is equal to 31,610 divided by 350 grams, and of course that should be joules, multiplied by 4.186 joules per gram Kelvin. And we can just do that calculation. That should be a little less than 10, divided by a little more than 4, so this should be a little under 2. But let's see. 31610. Oh, sorry, this should be a little, so it should be a little under 20. Sorry. And if we're going to use a calculator here, we got to be careful to put these in brackets down below, so it knows that we're dividing by the product of these two things. And what do we get? Yeah, 21.5. And how many sig figs do we have? Well, really only 2. So we'll call this 22 degrees Celsius is the change in temperature. Now be careful, because the question says, what's the final temperature? Final temperature. Well, we know this energy gets released, so if it started at 28.2 and it goes up by 22 degrees, we can just say, okay, well, 28.2 degrees Celsius plus 22 degrees Celsius is equal to 50 degrees Celsius. And that should be our final temperature. Cool. I think I threw some throwback stuff here. Lewis structure for silicon dioxide. Oh man. Silicon and oxygens. Oh man. How many valence electrons does silicon have? Well, 2 times 4 is 8 electrons. Oxygen is 2 times 6, so 16 electrons. There's no negative sign here, so that is 24 electrons. And we would say, okay, here's silicon, and there's oxygen, we put a single bond between all the above. We would go like that, and then we count 2, 4, 6, 8, 10, 12, 14, 16. Oh, what? Silicon dioxide. Silly me. What am I doing? Oh, see, I'm fired. I am fired. But we should have 16 electrons. There's only 1 silicon, and there's 2 oxygens, and silicon has 4 each, and 2 oxygens have 6 each, so we should have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. All right, good. But octet rule tells us that instead of that having those electrons by themselves, they should go there. Octet rule says that should go there. That should be silicon dioxide. Now, if we want to, we could also count formal charges. Don't worry about this if you don't. But oxygen here has 2 lone pairs and 2 bonds, so it has a formal charge of 0. This oxygen has a formal charge of 0. And silicon is making 4 bonds. It has a formal charge of 0. So this is a great structure. Everything likes it. If you didn't do the formal charges lesson, don't worry about that. Point being, we like this structure. That structure is good. What's the hybridization state of each atom? Well, this silicon is making 2 sigma bonds, and it's making 2 pi bonds. So that makes this sp hybrid. Right? It'd be sp3 if it was making all sigma bonds, sp2 if it was making just 1 pi bond, and sp because it's making 2 pi bonds. All right, we're good there. And these 2 oxygens are the same, so we can think about them at the same time. They have 2 lone pairs, they have one sigma bond and one pi bond, and that makes them sp2. What's the shape? Well, the central atom is sp, which means this is one-dimensional, so the shape is linear. Been a while since we've done that, eh? Energy level electron configuration of copper. I don't have a periodic table in front of me, so you're going to have to look that up. I don't know copper's atomic number off the top of my head. I guess I could figure it out really quickly. Atomic number of copper. 29. So copper has 29 electrons. So 1s will hold 2 of them. 2s will hold 2 more. 2p will hold 6, and of course I should follow Hund's rule and fill that at a time. So 2, 4, 6, 8, 10, so we're up to 10. 3s gets filled next, it takes 2, so we're up to 12. 3p is next, and it will hold 6, which brings us up to 18. After 3s gets filled, 4s will get filled, and it will hold 1 and 2. But then 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p. Okay, let's follow this along. So first we fill 1s, then we fill 2s, then we fill 2p, then we fill 3s, then 3p, then 4s, but then 3d. So now we're up to 20 electrons, and then in this spot we get 3d, 1, 2, 3, 4, 5, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is the electron configuration of copper. And if we want to write that out nicely, we'd say it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Let's just quickly add those up, make sure I didn't make a mistake, because I do that. 2 and 2 is 4, and 6 is 10, and 2 is 12, and 6 is 18, and 2 is 20, and 9 is 29. So that is copper's electron configuration. Ooh, been a while since I've done that. Right, and then what is the result of a reaction between propan-1-ol and ethanoic acid? Draw the reaction, be sure to name everything. All right, well, we can do this. Propanol is 1, 2, 3. Propan-1-ol means there's an OH there. The rest of these are all just hydrogens. That is propan-1-ol. You can draw that. And then ethanoic acid is ethane is 2 carbons. This one's just going to have hydrogens all over it. But here we have double bond O and bond OH, because that is a carboxylic acid group. That's where our reaction's going to happen, in fact, specifically thusly. So that's going to give us some water, because I see water there. Let's put that together. Whoa, there we go. So HOH. That is there. And then carbon, 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 bond to oxygen, carbon, carbon. That still has that double bond to O. And we need just hydrogens all over the place, just like that. And this would be considered an ester, right? Because it's got the O double bond to O on that carbon. So an ester means that this is the main group. It's an ethanoate. And this side is 3. So this is propylethanoate. There we go. All right. Whew. That felt like a lot of work. But hopefully that was of some help to you. I'm sorry that I had an audio problem again. I won't have that happen a third time. I know what I'm doing wrong now, so that's good.